Welcome, friends. A very good morning and a very good day to wherever you are. Today, we are going to discuss about the lesson alternating currents, which is indeed a very important one in view of CBSE boards as well as the other entrance exams such as JEE, NEET, to name a few. Okay, so this is undoubtedly one of the important and higher weightage carrying lesson in case of standard 12th. So without wasting any time, let us start with a few basics and then we will go into the deep detail one by one. Talking about the basic introduction in respect to alternating currents, in the previous lessons such as current, electricity, the first three which were basically regarding the static charges, now we are going to deal with, you can say, the alternating parameters of charges as well as current. Clearly, if a current tends to flow steady and in only one particular direction, it is clearly termed as a direct current. The limitations of direct current are of undoubtedly few, such as clearly they are only restricted to applied only in case of a few, like charging of batteries, electroplating, electric fraction. Likewise, if we tend to talk about a few of the advantages why we are in a need to discuss about the alternating parameters and why we need to discuss about the alternating current and alternating voltage. There are certain advantages of using an AC system. Clearly, the polarity tends to change after regular intervals of time, which is going to undoubtedly affect the direction of the current as well as voltage as well. So clearly, the generation, transmission, the TDP, transmission, distribution, and production, it tends to get largely affected with the help of alternating parameters. Talking about the basic representation of an alternating quantity, clearly we can represent it with the help of an equation V, where we will represent the instantaneous value of the alternating voltage equivalent to Vm sine omega t. Clearly, Vm will represent the maximum peak or simply the maximum value of alternating voltage. Omega will represent the angular velocity of the coil. Always remember that sinusoidal voltages, they produce sinusoidal currents unless the circuit is a non-linear one. So we are also going to discuss why we tend to only apply sinusoidal waveforms in respect to alternating quantities. We are going to discuss that later on. So this is the basic representation of representing alternating voltage and alternating current. Clearly, both of them are resembling the same sinusoidal waveform going into a positive half, having a maximum peak at Vm at 90 degrees because sine 90 represents the maximum value as +1, and similarly going in the other negative phase as well, having a peak minimum as minus Vm represented exactly at 270 degrees and returning back again to the same point. So clearly it represents a sinusoidal voltage. We can also represent the alternating voltages in respect of Vm cos omega t or Im cos omega t also, because sine and cos waveforms are largely similar. Undoubtedly their starting points are going to vary. Now the basic question arises why sine waveforms are generally tends to use not square waves, triangular waves or rectangular waves. Now there are a few primary applications as well as the reasons why sine waves are used for producing alternating voltages and currents. The basic reason is that it produces the least disturbance in the electrical circuit and undoubtedly the smoothest and efficient waveform. So whenever current flowing through a capacitor, any sort of load like capacitor or inductor or in a transformer, when it tends to be sinusoidal, the voltage across the element is also sinusoidal, which is indeed true only and only in case of sine waveforms, not in case of square, triangular or rectangular waves. Another main reason for using and applying the sinusoidal waves is that the voltage is applied to designed coils, basically on the basis of inductor coils. They result in revolving magnetic field which has the capacity to do work. So it clearly underlines the principle of applying the applications of inductions motor, which largely are used in day-to-day applications. To name a few, clearly we are using induction motors in case of the railway transmission system, in case of metros, more prominently Delhi metros. DMRC is also applying that application of induction motors using the, you can say, the flow of the alternating quantities. Although other waveforms can also be used, it is not only a compulsion that sinusoidal and alternating quantities you need to use, but it is the most efficient one and undoubtedly an economical one also. The main, you can say, advantage of using sinusoidal waveforms is that the mathematical computations. Further, you will be slowly and gradually learning about the various calculations involving the RMS value, root mean square value, peak value, average value, and different associated parameters related to the power calculation. Thereafter, you will study about the energy consumption and so on. So those mathematical computations are comparatively easier when we tend to consider the factor of sine or cos. So trigonometrically also it tends to be slightly easier for us to do the mathematical computations. Now this is just the basic, you can say, how we tend to obtain the alternating voltages and currents. There are primarily two methods. Undoubtedly, a lot of methods are also employed apart from these two by rotating a coil at a constant angular velocity, which many of you must have also read in the lesson of moving charges and magnetism. When you tend to place a rectangular coil or any shaped coil between a fixed pole of magnet. So undoubtedly torque is going to be incorporated and you are going to simply convert the mechanical work as an input to the electrical output. Another method can also be employed by rotating our magnetic field at a constant angular velocity, which generally is the case with the induction motors, which generally is the case with the AC generators, in which a rotating part tends to simply create the rate of change of magnetic flux, which indeed will clearly going to generate the alternating voltage and hence the induced current. So the first concept related to a few parameters like amplitude, time period, and frequency, we can again just have a quick definition for the alternating current whose magnitude changes continuously with time and direction clearly reverses periodically after each half cycle. So the basic representation for the EMF or the voltage will be E is equal to E naught sine omega t, and similarly using the Ohm's law you can also dictate I is equal to I naught sine omega t, where clearly I naught and E naught will represent their respective peak or the maximum values. Now amplitude can also be defined as the maximum value attained by an alternating quantity in either direction. It can also be plus E naught, it can also be a negative E naught. Negative E naught is definitely going to be in the, you can say, the negative half. Time period, a basic definition by time period you can easily compute as the time taken by an alternating current or a voltage to complete one cycle of its variation, generally denoted by capital T, and it will simply be the displacement 2 pi over a complete cycle divided by the velocity which is achieved. So in case of alternating quantities, we are representing the angular velocity with omega. The next definition follows regarding the frequency, which is simply the reciprocal. So it will represent the number of cycles completed per second by an alternating current. So it will be omega upon 2 pi, and hence we can modify the basic equation of alternating current as I naught sine omega t, inputting omega as 2 pi f, just cross multiplying this expression. So it can also be represented as I naught sine 2 pi upon capital T into small t. Always remember, when you are representing an alternating quantity, it tends to rise from 0 to a maximum in one particular direction, then falls to 0. Again, it is going to rise from 0 to the negative minimum and then again to 0. So then comprising a complete, you can say, representation for an alternating current or an alternating voltage. Mostly in Asia, we tend to have the frequency at 50 hertz, which is going to be a constant factor when you will be computing the calculations in respect to alternating parameters. The first of the, you can clearly place it under the category of derivations, that we need to prove that average value of an alternating current over one complete cycle is going to be a zero. So comparatively an easy one. Let us suppose we are considering alternating current flowing sinusoidally from 0 to a maximum of Im at 90 degrees, then to a minimum of minus Im, and then completing a one cycle. So alternating current can be represented as I naught sine omega t if you tend to simply assuming that current remains constant for a small time dt. So in that case, the amount of charge will be by the basic definition of I dt. So substituting current by I naught sine omega t, so the equation can be integrated to compute the total charges. Total charges will be required because by the basic definition of current, which is charge per unit time, we need to input that value in this particular parameter. So when you tend to integrate for the total charges, you simply need to substitute the value of I as I naught sine omega t. the time period is clearly going to be from 0 to capital T for a one complete cycle. So I naught, which will be taken as a constant factor, tends to get placed outside the brackets. So sine omega t will be integrated as minus cos omega t by omega. In putting, you can also substitute omega as 2 pi upon t. So that constant factor will be taken outside the sphere, and you when you tend to apply the upper limit to the lower limit, you are going to obtain a factor of a 0 only. So in that case, if total charges are 0 for a complete cycle, it is going to be undoubtedly no factor. So average value is going to be a 0. Now I again focus on the fact that we are calculating here for a complete cycle. When you will be computing the average value of a alternating current or voltage for a half cycle, you are going to attain a certain value. But for a complete cycle, it is always going to be a 0. A conceptual question is generally asked in this particular respect, that why ordinary MCGs, moving coil galvanometers used for DC, they cannot be used to measure the alternating currents if even the frequency is low. We can state the reason. Simple reason being, DC, which do not have the frequency variation, but in case of AC you tend to have bidirectional current. You tend to have a positive half cycle as well as a negative half cycle. So MCG, moving coil galvanometer, which is basically based on the direction of current. So that is why it cannot be used to measure AC, because in one half cycle it is going to simply point out towards the positive direction. During the next half cycle it will move in the opposite direction. So the average is always going to be a 0, as earlier mentioned, also with the help of a derivation. So even if a frequency is of a very low magnitude, the pointer will appear to be stationary. So alternatively, what you can use a hot wire ammeter, which is based on the heating effect. And it is going to be basically accumulating the, you can see the values of root mean square values, which we are going to be describing about and deriving also further in the lesson. Talking about the average value of an AC over half a cycle now, because for a complete cycle we have clearly observed that the value was 0. If we tend to establish the relationship between average and the peak value, we can do so. How? First of all, what average value means? It is simply the value of direct current which sends the same charge in a circuit if it is simply sent by the given alternating current in its half time period. So it is generally represented by IAV or IM, and if we tend to obtain the relationship between the average value of a AC for a half cycle, so we can approach likewise. Just what you need to do, you need to simply alter the limits. When you were computing for the complete cycle, you were taking 0 to capital T. For a half cycle, it will be T by 2. So integrate exactly in the same manner. In this particular case, what you are going to obtain? You are going to not obtain a 0. It is going to be I naught capital T by pi. So in this, if you tend to obtain the charges as I naught capital T by pi, average value is going to be simply sustained, because charge per unit time, you tend to put the value of Q as I naught capital T by pi. So common terms, capital T will get eliminated, 2 by pi. It will be equivalent to a factor of mathematical value of 0.637. So average value, or simply the, you can say the mean value, it is zero point 0.6 times the value of the maximum current. Similar observation can also be obtained if you tend to obtain the, you can say the average value of E, or simply the voltage. So EAV will be equal to 0.63 times of E naught. So similar parameters will be applicable when you will be doing for, you can say, the alternating EMF also. Now a very interesting fact is, when you have seen that the average value over a complete cycle was 0, because in that case waveform was symmetrical about the time axis. Exactly, the positive and negative areas were cancelling out each other. But for a half cycle, it is not a 0. It is simply 0.637 times the maximum value of the peak current or voltage, whichever you are taking. There is another alternate method you can use for the half cycle average calculation. How? You can also use the concept of area of integration. Let us suppose we are only taking a small displacement d theta. In that case, if current is represented by Im sine theta, you can simply have the area of the strip and evaluate the total. The total area of half cycle is only going to represent, you can say, the area of the particular region which we are considering. So if you tend to integrate id theta from 0 to pi over a half cycle, you are going to again obtain the same expression. Okay, we'll move on from this particular part of RMS value in the next class. I hope you must have gone through the content and you can clearly put up all your doubts, if in case any, in the comment section. Then we can particularly Whether it is regarding the definitions, concepts, or derivations, you can openly let me know. Then we will continue in the for the further topics like RMS value, for the more important topics of phasor diagrams in respect to the different types of load, resistive, capacitive, and inductive, and thereafter towards the rest of the lesson. Thank you so much. Take care. Bye bye.